Naming binary ionic compounds. When we have a metal that forms more than one cation, we have to include the charge. That's part of the ion's name. And so then the name will look like this, the name of the cation, parentheses, the charge in Roman numerals, and then the name of the anion. Really, it's the same idea. You name the cation, you name the anion. Okay? Some cations need a Roman numeral, some do not. Which groups do not need the Roman numeral? 1A, 2A, 3A, zinc and silver, right? So if the metal is in groups 1A, 2A, 3A, or it's zinc or silver, no Roman numeral. Because we can predict the charge from the periodic table. If it's any other metal, then we have to put in a Roman numeral. Well, how do you find the charge of that cation? You have to look at the charges of the nonmetal, the anion, and you have to look at the numbers, the relative numbers of atoms. Basically, you have to figure it out. Let's do an example. We're asked to name CrBr3. So we look at this and we look at the first element and we ask ourselves, is it a metal? Yes, chromium is a metal. And its name is chromium. So we write chromium, that's the element name. Then we ask ourselves, is it in groups 1A, 2A, 3A, zinc, or silver? No, it's not. We need a Roman numeral. I'm going to put the parentheses here, so I hold space. We don't know what that is yet. But I'm just putting a space there, and then I'm going to go on and name the anion. How would we name bromine as an anion? Bromide, yeah. We change the ending of the name to "ide." And so this is chromium something bromide. Now we go figure out what that charge is. And we do that by looking at the charge on the anion. So I'm going to do the picture method here. We've got one Cr and we have 3 Brs. We get that from the subscripts. 3 of these guys and just 1 of those. We can figure out the charge on the bromide from the periodic table. What is it? -1. So each of these is -1. The total negative charge here then is -3. If the total negative charge is -3, the total positive charge has to be +3 because ionic compounds are neutral overall. So we have a +3 charge, and it's going to be shared or distributed on just 1 chromium ion. So this gets all of it, 3+. Does that make sense? It's really hard to describe how to do that. When you see how it works, though, it's actually pretty simple. We're looking at how many of these and what are their charges and add all those up. Total negative charge. Total positive charge has to be equal. If there's more than 1 here, then it's going to be distributed, divided among them equally. And that's the charge here. So the charge of 3+ tells us that we're going to put a Roman numeral 3 in here, and the name is chromium 3 bromide. Any questions? Yes?
How do we know that it's going to be Br negative?
How do we know it's Br -1? That's a good question. So on the periodic table, there's different ways to think about it. One way is to start with the noble gases, and those are going to be 0. They don't form ions at all, and then count backwards. The next column over is -1, -2, and -3. And so we're just counting from krypton backwards, -1 to bromine.
Okay.
Question? Why are bromine and mercury blue on the periodic table? Anybody remember? They're liquids at room temperature. And the red ones are what? Gases, and the black ones are solids. What are the white ones? Man-made elements that are unstable. So they just like fall apart really fast.
So that would work.
That works for all the nonmetals, counting backwards from the noble gases. The other way to do it is to take their group numbers, 5A, 6A, or 7A, and subtract 8. Question?
Why can't we just make like a bunch of gold and then just have a lot of gold? Or is it like costing more?
So why can't we just make gold from other elements, right? Because it's possible. And that's what alchemy was all about. And we actually, science was advanced by people trying to turn things like lead into gold. It can be done, but it's not cost effective. The amount of money that you would spend doing that is way more than the gold itself is worth. And so, yeah, there's just no point in doing it. But it can be done. Any other questions? Here's a couple of other examples. So name this compound, FeS. We always start out by looking at the first element and asking ourselves if it's a metal. Because we're going to learn that there's two other categories of compounds that we're going to name. And we have to identify, is this a metal or a molecular compound or an acid? No, is it an ionic compound, a molecular compound, or an acid? And so by looking at the first element, we can generally tell. So Fe is a metal. This is ionic. So we're going to write the name for that element. Fe is the symbol for iron. Then we ask ourselves, is it in groups 1A, 2A, 3A, zinc, or silver? No, it is not. It needs a Roman numeral. So I'm going to leave space, and then I'm going to go on and name the anion. S would be what? Sulfide. Just taking the element name sulfur and changing the end of the name. I think of the nonmetals as being feminine, like women, and so, traditionally when a woman marries, she changes the ending of her name. She changes her last name. So these nonmetals change the ending of their name when they become part of a compound. So I guess forming a compound is the chemical equivalent of getting married. I don't know. So we've got iron something sulfide. Then we need to look at the different ions. Here we just have one of each. And we're going to look at the charge on the sulfur, which is 2 minus. So the total negative charge is minus 2. And the total positive charge has to be the same number, because plus 2 and minus 2 add up to 0. That's what we're looking for.
Why is it 2 minus and not 1 minus, since chlorine is a gas?
Well, chlorine is a gas, but it's not a noble gas. Okay, so the noble gases are group 8A. Helium, neon, argon, chromium, xenon, and radon. They do not form ions, and we'll learn why later. So those we consider would all have a charge of 0. They don't form ions. The next one over, group 7A, chlorine forms a minus 1 ion, because when it does that, then it has the same number of electrons as argon. And that's like a sweet spot for elements, if they have the same number of electrons as a noble gas. The reason that the noble gases don't form compounds is because they are very stable. Their electron structure is very stable. And so the other elements are forming ions or forming compounds to have an electron structure or the same number of electrons as the nearest noble gas. And so that's kind of the driving force between the formation of compounds. So sulfur's 2 minus. So total positive charge must be plus 2, so the iron must be plus 2. So iron 2 plus, now we know what Roman numeral to put in here. Any questions? Yes?
Why is it Roman numeral?
Why is it a Roman numeral?
Yeah.
instead of like an Arabic number?
Yeah.
Because I can make up reasons. I think it's because there are so many numbers that occur in all these other things, and we want this to be different looking. So we don't want this to be confused with a subscript or something else. It's sort of like, King Henry VIII. Why is the 8 written as a Roman numeral? It's fancy. It's about as good as because, right? So King Henry VIII. So apparently, Henry had a charge of positive 8. We know that what that means is he was the 8th King Henry, right? But if we wrote 8 here, like, what? King Henry VIII? What's that? And so basically it's just convention. It's just convention. Yes?
You put +2 on iron just because sulfur releases 2 electrons, right?
Yeah, what we'll learn later is what's happening is that sulfur becomes a 2- ion because it gained 2 electrons.
Okay, so that's what you put.
And so it gained 2 electrons because the iron gave it 2 electrons. We're not there yet, but we'll get there. I put the 2 here because I know that there must be +2 charge somewhere. So I look at the number. See, this is 1 iron and 1 sulfur. And so I drew 1 iron and 1 sulfur. I know the charge on the anion from the periodic table. And because there's 1 of them, I know the total negative charge is -2. Then the total positive charge has to be +2. There's only 1, so it has to have all of it. So we'll get rid of King Henry here. Let's do this one. Write the formula for ruthenium-4 oxide. It's always the metal and then the nonmetal, the cation and then the anion. When we're writing formulas, we have to write the formulas first with the charges. So ruthenium is Ru, and this is the Roman numeral 4. That tells us that the charge on this ruthenium ion is +4. It's not the number of them that are in the compound. It's the charge. And then I have oxide, that's O, and what's the charge on oxide? 2-. So I need to put these 2 together in a way that their charges add up to 0. That I get the total positive charge equal to the total negative charge. So we could do the crisscross thing, right? So we look at this, we've got 4 and 2, those are not the same. She said if they're not the same, we can crisscross. That's just taking this charge and giving it as the subscript for the oxygen. So O4, and then, I didn't mean to do that. This 2 being the subscript for the ruthenium. Are those charges going to add up to 0? Yeah, they will, because we have 2 times 4, so that's a total of +8. And then we have 4 times -2, and that gives us -8. +8 -8. We're good, right? What's the little glitch? We need the lowest ratio. When we look at this 2 to 4, that can be reduced. So it's actually RuO2. I wonder if there's a compound like this. What would that be? Are you okay? Here's another one. You see that one? That's what the Lone Ranger said to his horse. Hi-O Silver. So much geek fun. So any questions about RuO2?
I think there's another one that says, do you have any sodium hypobromite? Not RuO2.
Yeah.
The reason why we got 4 is just because it gives it to us? Or is there more?
This, why we got this 4 here?
Yeah,
That's because of the Roman numeral.
okay.
This Roman numeral tells us what the charge is. We need this Roman numeral because we can't figure it out from the periodic table.
Okay, so it's just because it's given, so I can give
It's
you
just
whatever.
given, yeah. So whatever the Roman numeral is, that's the charge.
And then for oxide, the 2 is because it's
2 over.
2?
Yeah. Yeah, and those are exactly the sorts of questions that you need to ask. You just keep asking them until the light goes on and you're like, okay, I see it now. And then what you have to do is you have to practice it so it sticks. Yes?
Is the first element generally positive in charge?
Yes, the first element will be positive because we always put the metal first and then the nonmetal. The metals always make cations. Metals do not make anions. And that's, you know, that works with my male-female analogy, that when you address a formal invitation, it's always Mr. and Mrs., right? Just because. And so it's always metal, non-metal. It's always cation and then the anion. Let's do another one. We'll make one up. My maker-upper is I'll do a cop-out and I'll do this one. Name it. Okay, so Fe is iron, right? Does iron need a Roman numeral? Yes. It needs a Roman numeral because it's not in groups 1A, 2A, 3A, zinc, or silver. Okay, you just chant that. 1A, 2A, 3A, zinc, or silver. Everything else needs a Roman numeral. And then O is oxide. Okay, so that part's pretty straightforward. We have to figure out what the charge on the iron is. Some of you can look at it and see it. So we've got oxygen and we've got iron. We have 3 oxygens and we have 2 irons. I'm just going to draw pictures so I can see what's going on. After you draw pictures a little while, then you can just do them in your mind and you don't have to write them out. We need the charge on the oxygen. We've been over that. It's 2 minus. Each of these is 2 minus. Oxide is always 2 minus. So my total negative charge is going to be minus 6. What's my total positive charge then?
4.
It has to be this same number but positive. Positive 6. So now I'm going to take this positive 6 and divide it equally among these 2 guys. What do they each have? 3. So this is 3 plus and 3 plus. And that tells me I need the Roman numeral 3 in the name. This is iron 3 oxide. Any questions? Yes?
So there's only iron 2 and iron 3.
There is only iron 2 and iron 3. But you don't actually need to know that. That's not something you have to remember. And like with tin, there's tin 2 and tin 4. There's no tin 3. Well, you don't have to remember that because you are going to encounter these either as formulas or as names. In the name, it tells you what the charge is. In the formula, you figure it out from the charge on the anion. And so you don't have to know which ones actually exist or not. You just need to be able to write formulas and write names. Okay. Any other questions?
In the formula, does it also tell you how many ions there should be? Because what I'm wondering is what keeps you from making 3 ions and then just putting 2 plus.
Okay, so if we had iron 2 plus with oxygen, well, if it was like this, I don't know what happened there. Now, this would be charge balanced, right? We've got -6 and +6. But why don't we have Fe3O3?
Because it's Fe2O3?
Yeah, this is Fe2O3, and this would be Fe3O3, and we would never write it this way because that's not the lowest ratio. It would be FeO.
Okay. Oh, because it would cancel?
I want that to go away. Stupid notification. If we had these 2 ions, we would look at them and we'd say, well, this is +2 and this is -2. I just need one of each of those to be neutral. And so we're always the lowest ratio. Here, this is Fe2. That means there are 2 irons. It does not mean that the charge is 2. And these are important things.
The train disagrees.
It's just one of those days. It's a Monday on Thursday. Any other questions? I don't know what it's doing. We did that. Let's see that. Okay, polyatomic ions. So polyatomic ions have many atoms within the ion. And you just have to memorize their names and formulas. We already did that, didn't we? And I've given you 2 quizzes on it. So the reason that these must be memorized is that there's no simple reason behind what the formulas are. Okay? There are reasons that nitrate is NO3 minus and not NO4 minus. But there's no simple pattern that you can use. The easiest thing actually is just to memorize them. I know what they are just because I've used them so many times. It's not like on the periodic table where I can say, well, just count backwards from the right side, or the charge is equal to the group number, or something like that. There are some patterns in these polyatomic oxyanions, but they don't make any sense to me. It doesn't help me out, and I figure if it doesn't make any sense to me, I'm going to have a hard time explaining it to you, and it probably won't work for you either. My husband sees a pattern in it, and that's awesome for him, but I don't get it. So I'm not going to do anything with it. So we just have to memorize them. These are ions that are known to exist experimentally, and we had to call them something. And so we gave them names. And just like you memorize the names of your siblings or the names of your friends, we just have to memorize the names of these ions. So here we have an example of a compound containing a polyatomic ion. So there's sodium, and there's nitrogen, and there's 2 oxygen. What's important to understand is that in this class, all of the compounds we're going to name and write formulas for that are ionic have only 2 ions, 1 cation and 1 anion. There are compounds that are not like that, but we don't have to worry about them yet. So sodium is the first one, and then everything else is the second ion. So all of these ionic compounds, we can cut them into two pieces, the cation and the anion. Sometimes students try to get a little creative, and they'll pull it into 3 parts, and they'll say this is sodium nitrogen dioxide or something. Well, that's all nice, but it's wrong. 2 ions. So the first ion is the metal, the cation, and the second ion is everything else, and it has one name. The name of that ion is nitrite. The reason the name is nitrite is because that's what everybody agreed to call it. I don't have any better reason for you. I'm sorry, I wish I did. But we decided to call it nitrite, and so everybody just has to call it nitrite. So this then is sodium nitrite. Sodium doesn't need a Roman numeral. These are some of the common polyatomic ions. I made you memorize most of these. Some of them have some alternate names. Hydrogen carbonate, its older name is bicarbonate. And bi was a prefix that meant hydrogen. And so hydrogen sulfite was also sometimes called bisulfite. And hydrogen sulfate is sometimes called bisulfate. So you should know that that exists. If you see it, you should, go look it up or something. But I won't expect you to know the ones in parentheses here. I prefer the name hydrogen carbonate. Hydrogen carbonate is carbonate with a hydrogen ion. So let's look at how that would work. Looking at the periodic table, what kind of an ion would you predict that hydrogen would make? +1, because he's over there with the group 1 ions, or metals, right? He's not a metal, but he does form a +1 ion. So we've got hydrogen ion, and we have carbonate ion. And if we put these two together, you just write the hydrogen first, and then the CO3, and +1 and -2, that's going to add up to what? -1. So this is hydrogen carbonate. The reason the charge is 1 less than carbonate is because it's got a hydrogen ion on it. And the same thing happens with sulfite and hydrogen sulfite. You add the hydrogen and the charge gets closer to 0. Sulfate and hydrogen sulfate. And then there's phosphate. Phosphate has a -3 charge. You put 1 hydrogen ion on it, now it's got a -2 charge. You can put 2 hydrogen ions on it, and now it has a -1 charge. This is called dihydrogen phosphate because it has 2 hydrogens on it. Okay? But mostly, you just memorize them because. The polyatomic ions that have oxygen in them, which is most of them, are known as oxyanions. They're anions that have oxygen, oxyanions. There are some patterns among the names of the oxyanions, but there's still some memorization that you have to use. So when there are 2 ions in the series, the one that has more oxygen atoms is given the ending -ate, and the one with fewer has the ending -ite. So nitrate and nitrite are very similar. The only difference is the number of the number of oxygen atoms. Number of nitrogens is the same, the charge is the same. Here's sulfate and sulfite. The only difference is the number of oxygens. So the names are very similar and the formulas are very similar. Yes?
So on that one, NO3 is nitrate, but then SO4 is sulfate. Why they couldn't have made it so like 3 oxygens would make ite or something like that?
Yeah, and this was a question that I got yesterday in the 1-minute paper. Why do some 8s, I call them the 8s and the ites, why do some 8s have 3 oxygens and some have 4? Guess what my answer is? Because. So my best guess is that I know that with sulfate and sulfite, there's only 2. There isn't one that has 5 oxygens. There isn't one that has 2 oxygens. And so we've got the 8 and the ite. With things like chlorine and bromine and iodine, there's actually 4 in this series. And so what we want is the 2 most common to be the 8 and the ite, because they're nice and short names. And then we have a prefix that we put on if we've got more or less than these, and that makes the name longer, and we want to avoid long names. That's the best I can come up with. Yeah, I know students would prefer that like all the 8s be O3, but they aren't, and it's not going to happen, and so we just have to accept it. The charges are different too. So more than 2 ions in the series. So this is chlorate, and this is chlorite. This is hypochlorite because it has 1 fewer than chlorite, and perchlorate has 1 more. So chlorine forms this series. The difference between these 4 ions is the number of oxygens, number of chlorines, charge is the same. Chlorine and bromine are element sisters. They're in the same family on the periodic table. They behave in very similar ways. So chlorine forms an ion with 3 oxygens and a negative charge. Bromine does the same thing. This is chlorate, this is bromate. Bromine also forms these other ions just like chlorine does. Iodine does that as well. And so there's another series with iodine. So we could have IO3 minus. Guess what the name of that one is? Iodate. So the beginning of the element name and then that suffix ate. And so iodite, hypoiodite, periodate, they're following the same pattern as chlorine and bromine. So there's a nice organized pattern thing for you. Unfortunately, they're not all going to work that way. So this is how I think about these guys. Memorize the 8s. So I live in Reedley, and the train goes through Reedley, small little town, and it usually comes through at like 3 or 4 in the morning. They sound their horn like that. They roll up the sidewalks at 9 p.m. in Reedley. There is no one out in the middle of the night except the gangbangers on the other side of town. But there's nobody out. There's nobody crossing the tracks. But the guys honk the horn like you would not believe all the way through Reedley. So people, of course, complain about this. The more you complain, the more they honk their horn. It's just, yeah. So imagine that, 3 in the morning. See, now he's done. Shut up. Okay. So memorize the 8s. What are the 8s? Those are all the ones that end in 8. Nitrate, chlorate, carbonate, phosphate, sulfate. Those are the big ones. And then learn the pattern. So here's the pattern. You memorize this one. You memorize the 8. The ite is the light version. It has 1 less oxygen. Same charge. Everything else is the same. 1 less oxygen. What's the difference between Bud and Bud Light? Bud Light has 1/3 fewer calories, right? Commercials. Chlorite has 1/3 fewer oxygens than chlorate. It's the light version, fewer oxygens. Okay? Per. Per is part of like hyper. What does hyper mean? Above, more. Hyperactive, more active, right? Perchlorate has 1 more oxygen than 8. You memorize the 8, you can figure out perchlorate, perbromate, periodate. And then hypo. Hypo is a prefix that means below. Where does the nurse put the hypodermic needle? Below your skin. Dermic refers to your dermis, your skin. A hypodermic needle goes below the skin. So hypochlorite has one less oxygen than chlorite does. So there's a pattern here. So for chlorine, bromine, and iodine, you memorize chlorate and the pattern, and you can write the names and formulas for 12 polyatomic ions. That was a really long train. So this is nitrate because it is. That's an I. What's nitrite? NO2 minus. One less oxygen. Because there is no hyponitrite. But if there was, we could write the formula for it. I don't expect you to know which of these exist. You just need to know how to name them. If there was hyponitrite, what would the formula be? NO negative. So hypo means below, per means above. So that doesn't actually exist, but it's okay. So, you know, I know a lot of people seem to be interested in why. Why don't we call this one sulfate? Well, if this was sulfate, then this would be persulfate. And I think it really goes back to history, and for most of these there were two. And so 8 was the one with more oxygen, and 8 was the one with less. And they did similar things with the metal cations. There was ferrous and ferric. One is the higher charge and one is the lower charge. Doesn't tell you which ones are, but you have to remember it. Yeah.
So for those, is the top one sulfate and the bottom one sulfite?
Yes. So this is sulfate and this is sulfite. You have to just memorize that this is sulfate. It's got 4 oxygens and a -2 charge. And like I said, there's a reason behind that, but it's not a simple reason that I can explain to you right now. Any questions? So let's name this compound. First element, tin. That's the first ion. I was thinking SN means tin, and so I started to write SN. Does tin need a Roman numeral? Is it in groups 1A, 2A, 3A, zinc, or silver? It is not in those, and so yes, it needs a Roman numeral. It's not a transition element, is it? It's a main group element. But it's not in groups 1A, 2A, 3A, zinc, or silver, so it needs a Roman numeral. So over here, this is going to have one name. We can't call it chlorine trioxide or anything like that. It has a special name because it's a polyatomic ion. What's the name of it? Chlorate. Why?
It's one perchlorate and then chlorate and chloride.
Because chlorate is ClO3. Because. Yes? The 2 or the 3?
The 2.
Does the subscript 2 affect the name? No, it doesn't. There's parentheses on this one, right? We haven't seen those yet. Why are there parentheses there? Because there's 2 of them. So if we wrote this without the parentheses, that looks like 1 tin, 1 chlorine, and 32 oxygens, right? Is that what I meant? No. We put parentheses around polyatomic ions when we have more than one of them to avoid confusion like that. So this reminds me of shopping at Costco. You go to Costco and you want a bottle of ketchup. Can you buy one bottle of ketchup? No. There's two of them and they're shrink wrapped together. And they're big too. Sometimes you can buy one of something, but it's ginormous. Like the 50-pound bag of rice, which we do buy and we go through it just fine, thank you. But you can't just buy one of a lot of things. You know, if you want to buy a game system, you can't just get the game system like you could at Target or something. It's going to come bundle packed with like 2 games and an extra controller or something, right? And they're shrink wrapped together. I think of the parentheses in these formulas as being like the shrink wrap. We're saying this is a unit. The chlorate is a polyatomic ion. It stays together, and we have 2 of those things. Okay? Whenever you have more than one of a polyatomic ion, in the formula you put parentheses around it, and you put the number on the outside. The number 2 here is not going to affect the name of that because this is just telling us how many there are. Just like when we had, like if we have Fe2O3, the 3 does not affect the name of the oxide. It's still oxide. You have a question?
For the 2 subscript outside the parentheses, does it only affect the chlorate or the formula as a whole?
It only refers to the chlorate.
Okay.
So this number 2 tells us there's 2 of everything in the parentheses. It does not apply to the tin. It's just what's in the parentheses. 2 of these shrink-wrapped packages. This 2 is important because for this one with tin needing a Roman numeral, we need that number 2 so that we can figure out what the charge on the tin ion is. So I'm going to draw this out in picture form again. So I have a chlorate ion, which has what charge? -1. And I have another one with a -1 charge. Because this 2 subscript tells me there's 2 of everything inside the parentheses. So I have 2 of those. Total negative charge here is -2. There is only one tin ion, because there's no subscript after it. My total positive charge has to be the same number as my negative, because these have to add up to 0. Total positive charge is +2. There's only one tin ion in there, and so it must be +2. And then my Roman numeral will be tin 2 chlorate. The Roman numeral distinguishes this from another compound, which is tin 4 chlorate. That has a different formula. See, there's a unique name. Unlike humans, where you can have multiple people with the same name, even the same middle name, I had 2 students in one class that had exactly the same name. First, middle, and last, their names were the same. That was confusing. With compounds, when I say tin 2 chlorate, there is only one tin 2 chlorate. There's not multiple different ones. There's one. Okay? And so we have to be precise, because if we get sloppy, then we don't know what we're talking about. You know, we need to be able to communicate. Because sometimes, like with carbon dioxide and carbon monoxide, one thing is harmless and another thing is very toxic. What would the formula for tin 4 chlorate be? Well, the SN then is going to have a 4+ charge, right? And then we've got chlorate with a -1 charge. So we're going to need 4 of the chlorates to balance the charge on the tin. And so the formula is different. The formula is different, the name's different. Any questions about that one? Write the formula for cobalt 2 phosphate. What's the formula for cobalt 2 ion? Need the element symbol, right? CO. You gotta be careful with your sizes there, because C capital O, that's carbon monoxide. C lowercase o is cobalt, which is a metal. They're really, really different. What's the charge on the cobalt ion? 2. How do we know that? Because the Roman numeral tells us. Isn't that nice? We need the Roman numeral because the periodic table isn't going to help us on that one. Then phosphate, what's the formula for phosphate? PO4, 3 minus. So, you were supposed to memorize these, and most of you did a pretty good job with that. Keep your flashcards, keep looking at them. When you do problems like this, do not immediately go to your cheat sheet, your card with, all the stuff on there. Try to do it from memory first, and then check yourself. And that way you'll get it correct, but you'll also reinforce your memory. It's like making a cow path in the grass. I went to Iowa State University as an undergrad, and they had built some new buildings and stuff, and there's this big green area, and there were no sidewalks. It's like, what the heck? So, you got to get from one place to another, so people just walk through the grass. What they were doing was waiting to see where people were going to walk, and then they put the sidewalks there, right? Because enough students walk on the same path, they kill the grass. In Iowa, that's called a cow path. And how do you kill the grass? By going over the same area again and again and again. And if it gets trodden down hard enough, the ground gets packed, and even if you stop walking on it, it'll take a long time for grass to grow there again. That's what you need to do in your brain. You need to make cow paths in the grass of your brain. And you do that by just doing it over and over and over again. You just don't want any cow pies in there. So, how do we put these two together? There's 3 different methods. You can draw pictures, you can do crisscross, or you can do algebra. So the crisscross way is you take this 2, that becomes the subscript for the phosphate, and the 3 becomes the subscript for the cobalt.
So would you multiply the 2 and the 4? Okay.
That's a good question. So would I multiply the 3 and the 4? No. What I want to do is put parentheses around that and put, not the 3, the 2 on the outside. Because I want to show that I have 2 of those phosphate units. Now, if I wrote CO3P2O8, in a way that indicates the same thing, but it's harder to see that this is 2 phosphate ions. This gives us the correct number of cobalt atoms, phosphorus atoms, and oxygen atoms. But it's hard to look at, and it's hard then to name. Okay, so we don't do it that way. If you have more than one polyatomic ion, put parentheses around it, shrink wrap it, and say on the outside how many of them you have. Any questions? Hydrates. We're not going to do a lot with hydrates, but you just need to know that they exist and how to name them. So hydrates are ionic compounds that have specific numbers of water molecules associated with each formula unit when they crystallize and form a solid. So this is the formula for Epsom salts, which you may have used to soak a sprained ankle or something. For every 1 MgSO4 formula unit, there are 7 water molecules that are in the crystal. This is different than, just sprinkling some water on table salt. That's not a hydrate, that's a wet salt. This is a specific number. It's a compound because the proportion is the same throughout. So we name this by naming the ionic compound first, and then this dot with the number and waters, we use a prefix to indicate the number, and then the word hydrate to specify the water. So this would be magnesium sulfate, magnesium sulfate, heptahydrate. Hepta is the prefix that means 7. This dot just means that these are associated with each other, they're part of the same compound. It does not mean that we're multiplying anything. That's what the dot means in math. That's not what it means in chemistry. So this one's COCl2 dot 6H2O. This is cobalt 2 chloride. Cobalt needs a Roman numeral. Cobalt 2 chloride hexahydrate. These are the prefixes, and you need to know these. Not for the first exam, but for the second exam. So hemi means half. A hemisphere is half of a sphere, right? The northern hemisphere. It's the northern half of the planet. Mono means 1, di is 2, tri is 3, think triangle. Tetra might be a little unfamiliar, but if you think about tetras, those shapes that are being dropped in tetras always have 4 squares in them. Maybe you didn't notice that, but it's true. Penta, like a pentagon, 5. Hexa, like hexagon. Hepta is weird. Hepta means 7. And then octa is 8. So how would we name this guy? CaSO4 dot 1/2 H2O. Calcium sulfate hemihydrate. So calcium sulfate, calcium does not need a Roman numeral. So calcium sulfate, and then the prefix hemi for half, and hydrate. How about this guy? Barium chloride. Barium doesn't need a Roman numeral. Hexahydrate. How about this one? Copper 2 sulfate hexahydrate. What would that be? So we have to think about the charges. Copper 2 is Cu2 plus. Sulfate is SO4 2 minus. So it's just one of each. And then a dot and 6H2O. Any questions? That's a good question. It's not half of a hydrogen, it's half of a water molecule. How can you have half of a water molecule? Good question.
One hydrogen molecule, half of an oxygen.
No, because you can't have half of an oxygen atom. You can't have half of a molecule. What's really going on here is this, the ionic compounds formula is always the lowest ratio. And so what it really is there's one water molecule for every 2 of these. But because of the convention, we're not going to have a number in front of this, and so that ends up being half. Does that make sense? It's really, there's 2 calcium sulfate formula units for every 1 water molecule. Okay, so there is no half of a water molecule. Any other questions? That was a good question, huh?